Welcome to the Exam 1 Review Problems video. In this video, I'm going to be going through the solutions to a couple of additional problems in order to help you in your preparations for the upcoming exam. Hopefully, these problems are things that you can solve on your own, but I'm here to provide a little bit of extra help, a little bit of extra guidance through the solutions to these to help push you in the right direction. So let's go ahead and get started with this first one. If you have not had a chance to try this problem yet on your own, I would encourage you to attempt the solution now, pause the video, see if you can solve the problem on your own, and then come back and look through my solution. All right, so let's go ahead and get started. We are trying to determine the solution set to this system ax equals b for the given coefficient matrix A and right-hand side vector b. So we're solving a system of equations. Another way that we can think of this system is by augmenting the coefficient matrix with this solution right-hand side vector. So we're going to have 0, 1, -1, 0, 5, 1, and 0, 2, 1. Augmented with -2, 8, and 5. Now, notice this one right here, that's going to become a pivot for us. So we need to clear out everything below it. So for the first couple of EROs, I'm going to add first row to second times -5 to get rid of that 5. And I'll also add first row to third times -2. So this will give us 0, 0, 6. The augmented component is going to be 18. And then the third row, we're going to get 0, 0, 3, and 9. Now, from here, you might already be able to tell that the second and third rows are multiples of each other. So the precise order of the EROs you use or which EROs you use won't really make a difference in the solution to the system. So we can solve this using any order of EROs that we like. I'm going to go ahead and multiply the second row by 1/6. So I can get my next pivot right there. So that's going to be 0, 0, 1, 3. And now I can use that second row to get rid of the third one by using that addition operator. So add second to third row times -3. So we get 0, 0, 0, and 0. So we have a row of all zeros down at the bottom, and we have our two pivots. So the pivots are going to correspond to leading variables. So if each of these columns pertains to a variable, so we'll say x, y, and z, the columns with the pivots have the leading variables, which means that we can get specific values. So like this equation right here is telling us that z equals 3, and that's our solution for z. This row is now telling us y minus z equals -2. And since z is 3, that gets subbed in here, add that over, and we have y is 1. The first column, however, corresponding to this x value, this doesn't have any value listed. It's an all zero column. The common misconception is to think that this means that x has to be 0 because we see the zeros and we think that that means it is 0. What this actually means is that x is not specified in any of the equations in this system. So x can literally be anything, can be any real number. and it will not change the solution set to this system whatsoever. And this is what we call a free variable. So x will be t, which is a free variable. And again, that is because it is in an unpivoted column. So because there is a free variable present, that does mean that we're going to have infinitely many solutions. And the question is asking for the solution set. So the solution set is going to be all ordered triples, x, y, z, of the form t, 1, 3, such that t is a real number. And that would be our solution set. So again, this does form infinitely many solutions because you can take any real number for t. So if t is 0, the point 0, 1, 3 would be a solution to this system of equations that we have set up here. And if t was 10, if t was 1,000,000, if t was, negative 1,000,000 or 1/2 or any real number, it would produce a new solution for this system of equations. Now, looking down at the bottom here of the page, the question asks, in the problem above, is A invertible? Justify. Well, we definitely want to refer to the invertible matrix theorem. That's going to give us many different equivalencies and like co-requisites for invertibility, and see if any of those either succeed or fail given these conditions. And there are a couple options that we can use in this case. Option 1 would be to look at the system itself. So since the equation ax equals b does not have one unique solution, by the invertible matrix theorem part B, A is not invertible. So this is one of the equivalencies to a matrix being invertible, is that this system does need to have one unique solution, and we just finished showing that it had infinitely many. So that means that the matrix cannot be invertible. Another possibly faster way to recognize this would be to look at its rank. So since the rank of A, this is the number of pivoted rows or columns in the matrix. The rank of A was 2 here, right? We had 2 pivots. The size of the matrix, though, is a 3 by 3. So this is not equal to n, which is 3. In order for the matrix to be invertible, the rank does have to be equal to the number of rows or columns. So by the invertible matrix theorem, part D, A is not invertible. All right, moving on to the next problem. Use the adjoint theorem to find A inverse given this 3 by 3 matrix A. So if you haven't had a chance to attempt this problem yet, go ahead and pause the video now and do so, and then we will begin the solution momentarily. All right, so in order to find the value of A inverse using the adjoint theorem, we're going to need the determinant and we're going to need the adjoint. So the determinant we can get relatively quickly here. The method by which you want to get the determinant would be up to you, because this is a 3 by 3. We have some leeway here. A cofactor expansion wouldn't be too bad because you would have this column with 2 zeros in it, so you could just use the 5 and do cofactor expansion on the second column. Or because it's a 3 by 3, we could use the arrow method and go through the diagonals there. But either way, however you prefer to do that, you should get a determinant of 25. So we're going to kind of tuck that away for later. We're going to need that at the end. In order to get the adjoint of a matrix A is going to be the matrix of cofactors transposed. So we're going to need the matrix of cofactors. So the matrix of cofactors is the matrix whose components are the cofactors of the original matrix components. So the cofactor of the 1, 1 position becomes the new 1, 1 position, etc., all the way across. So we're going to need the matrix of cofactors here. So let's go ahead and try this out for a few examples here. So for C11, so the cofactor, we're going to take -1 to the 1 plus 1, which if you recall, that is all dependent on its position, right? We have that checkerboard pattern that goes across here that can let you know whether this term keeps its sign or flips its sign. So that can be a helpful tool. In this case, it's going to keep its sign because this is -1 squared, but that's going to be times the determinant of the remaining 2 by 2 submatrix when you block off the row and column of this term. So that's 5, 3, 0, 1. So we get, this is a +1 times, this is 5 minus 0. So that's just 5. So the cofactor of the 1, 1 position is 5. So that's what goes into the matrix of cofactors. If we slide over 1, we're going to get -1 to the 1 plus 2. So that'll be -1 here, times determinant of, block off row and column, 4, 3, -1, 1. So we're going to get negative, and then that's 4 minus -3. So that's 4 plus 3, which is 7. So we get -7 for the 1, 2 component. If we do the C13, so again, we're going to get a +1 here, times the determinant of 4, 5, -1, 0. So we get -4 minus -5, or excuse me, positive 4 times 0, so that's 0 minus -5, which is +5. So that one also gives us a 5. And if we were to continue on in this process for the other 2 rows, the values we would get 0, 5, 0, and 10, -29, and 35. So this would be the matrix of cofactors. The adjoint of A is the transpose of this matrix. So we're going to interchange the rows and columns of the matrix. So you can visualize that, as this row becomes this column, etc., or you can think of it the other way, like this column becomes this row, etc. But either way, so we'll get 5, 0, 10, -7, 5, -29, and 5, 0, 35. That is the adjoint of the original matrix. And now the adjoint theorem says that A inverse can be found by taking 1 over the determinant of A times the adjoint of A. So in this case, that is 1 over 25 times 5, 0, 10, -7, 5, -29, 5, 0, 35. And that is A inverse. You certainly could multiply the 1 over 25 in to every component if you want to get the coefficient away from the front of the matrix and just multiply it in. It does simplify down with most of the terms. So if you wanted to do that, you certainly could, but you also certainly do not have to do that. It is perfectly equivalent as is. All right, but that brings us to the end of these couple of practice problems. So hopefully your solutions are looking good when compared to these, and hopefully this is all starting to make sense to you. I wish you the best of luck with the remainder of your preparation for this upcoming exam, and I will talk with you all very soon.